any further ado, please join me to welcome Dr. Gavin Wood.
Thanks, Obi. Hello. Is this the one? Yes. Hello. Thank you for the welcome. This is the, what are we on now, 7th in the series of lectures at various academic establishments about JAM, the Join Accumulate Machine. I want to, I'm going to get on because I've got some new stuff, some new material, and I don't know how long it's going to take to show. Good. I'm thankful to Ovi for giving the context with which this talk comes to you. I want to begin by drilling down a little bit on that context. Within the blockchain sort of Web3 industry, we see a growing divide between what we might call the long-term thinking that Bitcoin, to a large extent, but also protocols prior to Bitcoin, really embodied, and shorter-term results that are much more driven by, well, lesser ideals, I would say. And we've seen some of the things that short-term results result in quite recently with the Bybit hack. I was giving this presentation, by the way, this very same slide, more than 5 days ago, teaching people that maybe it's not such a good idea to emphasize short-term results over long-term thinking. Maybe it's better to have secure, rich metadata when we're signing transactions rather than just assume that the hash is probably fine and sign anyway. And then, yeah, it turns out that 1.5 billion gets nicked because of that. We cannot expect things to be fine if we prioritize short-term results in favor of long-term thinking. They will not be fine. A few practitioners will certainly make off with a nice, tidy profit, but the wider world, the wider industry, the user base, the companies building businesses on these things will not. Polkadot is really at the forefront here in creating software, services, protocols, and products which have the long-term thinking at their heart. Now, these four things are not the same. They're related to some extent, but they're far from the same thing. You know, cryptocurrency is essentially a virtual resource. Blockchain is a technology, pretty much the only technology which we know can implement this in a secure, fundamentally secure fashion. DeFi is a vertical, another use case, if you like, built on much the same technology. But Web3 goes beyond blockchain, and it certainly goes beyond DeFi or any particular use case of it. Web3 is an approach to solving problems. In some sense, you could say Web3 is the basis for building resilient public digital infrastructure. Now, the key difference between Web 2 and Web3, in fact, not just Web 2 and Web 3, but pretty much everything that has come before Web 3 and Web 3, is that Web 3 systems are designed to be resilient. In some sense, they're designed also to be anti-fragile, such that diversity actually improves the system, improves its resilience, makes it stronger. This is in stark contrast to traditionally architected systems, server-client systems, centralized systems, Web 2 systems. This resilience has to be against everything, not just a selection of things, including the things that we don't know about yet, unexpected situations. So in this way, Web3 is a revolution in how we interact with the world, how businesses interact with each other, and so on. Now, the main resource of Web3, you might argue, is block space. I'm not actually sure whether it's the only resource. I suspect that we could argue that there are things like secure messaging or authentication, systems or, I don't know, decentralized storage systems that could also be argued to be a resource of Web3. But certainly the main resource of Web3 is block space. And a quite respected person within this industry reckoned that it was actually a pretty good thing to be selling. Reckoned that, you know, this was something that would become a very strong need for. Now, block space isn't just all the same type of stuff. There are various different qualities of block space. Yeah, it has certain properties that we can measure it by. Blockchain is in fact a decentralized computer. That's all it really is, a decentralized computer. Now, a decentralized computer is a bit of an odd thing because computers, at least the ones that you're probably familiar with, are quite physical. Like, here's a computer, it sits here in my hand. It doesn't sit anywhere else. I can take it with me and make it sit somewhere else, but then it doesn't sit here. A decentralized computer doesn't have a physical form. It's actually just a model. But it's a model that is real in the sense that we can use it, in the sense that it has a definite state. And because it has a definite state, we can give it a sort of name, and we can tell other people that we're using it too. We can deploy software and expect other people to be able to use that software. So it is a single computer. It's just not a single computer that happens to have a body. That's all blockchain is, really. And the fact that it's decentralized is what gives it some of these properties that we like to see, like resilience. Now, history has a habit of repeating itself, or at least rhyming with itself. We see usually, if we look through history, a particular narrative play out as new technologies are introduced. Initially, those technologies tend to be very domain specific because they're there. There was a problem that was economically important enough, economically pressing enough, that new technology had to be invented to help solve it. Yeah? That implies that there was a particular domain, a particular problem that the technology was created for. Over time, that technological advancement tends to be reused or reapplied to solve other problems in other domains. And we end up with a collection of different related solutions, all basically using the same underlying technology. Before long, there generally tends to be a generalization or an abstraction of the technology that allows the very same piece of technology to be used to solve all of these problems. Yeah? This happened with computers. The initial computers were very domain specific. They were basically calculators that were built to solve particular problems, particular mathematical calculations. And over time, the mathematicians that were using them thought maybe they'll generalize them so that they can compute any kind of mathematical calculation. Before long after that, those mathematical calculations got very complicated and turned into basically business services. So this initial invention to generalization is a pretty standard step. Now, one of the other steps that we tend to find is economic commoditization coming after generalization. Once something's general enough, we usually have a few different, very generalized competing technologies. Over time, they tend to converge. And instead of having competing generalized technologies, like, I don't know, probably this is going to fall on deaf ears, but VHS versus Betamax, we tend to converge on a single technology, a single standard, if you like, but with many vendors. Now, blockchain has not yet gotten to that point, but regular computation, regular kind of server-based computation has, and we call it the cloud. We have many different vendors for the cloud, but we can generally choose which one and deploy our software to whichever one that we want. Instead of competing on the specific standard of the industry, they instead compete on relatively smaller differentiators. Blockchain is doing this, right? Blockchain started as a very domain-specific solution with Bitcoin. And over time, it has been generalizing. It's still in the generalizing phase, but eventually we will see some sort of commoditization. Now, one of the sort of steps that blockchain went through was in its journey of generalization was Ethereum. With Ethereum, we aim to take the scripting language, essentially, that Bitcoin had, Bitcoin script, and turn it into a much more general kind of language, a notionally Turing-complete language. Indeed, EVM is Turing-complete, the Ethereum virtual machine language. Now, Ethereum itself isn't very general. It imposes a number of very particular constraints on software developers that want to develop for it. But the language, at least, is pretty general. I mean, it's very nuanced, but it is in some sense mathematically general. With Polkadot, we move things forward a gear, aiming to create what we would call a cloud supercomputer, really trying to commoditize this stuff, create enough of it that is general enough that we could reasonably call it a commodity and allow general software to be deployed into it. So, Polkadot is designed to create the highest quality block space. We can measure this block space, as I said, in a few different ways. One of them is kind of performance or speed, or the amount of computation that it can do, or the amount of data that it can combine with the amount of data that it can take on. One of the not so effective ways of measuring, slightly gameable way of measuring how fast a block space or a blockchain can produce block space is transactions per second, which you might be familiar with if you know about this industry. Essentially, it's the number of transactions, a number of transfers of funds that can happen that a blockchain system can process per second. In a fairly recent performance benchmark, the production network Kusama, which is built on the Polkadot technology, managed to gain a pretty high transactions per second score compared to most other blockchains, well, indeed all other blockchains. And this was not at full capacity yet. We hope to try it at full capacity at some point in the not too distant future. Polkadot has the highest bandwidth in terms of megabytes per second that it can store and provide. And unlike other blockchains, Polkadot actually does have this as an inherent service that it provides. This actually outperforms domain-specific blockchains whose only job is to provide data storage. It's the most decentralized in terms of the nodes that are running it. The Nakamoto coefficient, a scoring, essentially denoting the number of economically independent entities that would have to be colluding or compromised before the blockchain started breaking, is by far the highest of any major blockchain, 5 times higher than the next. Ethereum's not actually on this graph because it's really very low. It's I don't know, 3 or 4 or something at the moment. It's also the most energy efficient. Now, energy efficiency, when we're talking about the relative sums of money that are going through, might not seem so important, but in reality it is. It's only by being energy efficient that we can reasonably hope to scale. The level of energy efficiency also caps the amount of transactions, or at least the cost of a transaction. We can never do, a Web3 system can never provide transactions for less than the energy cost, at least not long term. It achieves this through parallelization, distributing the workload across various different nodes on the network. This is in contrast to most other blockchains, which instead try to get every node to process everything sequentially, very notably Ethereum, but others as well. It shards data, but it also shards execution. It provides shared security, which essentially allows different economies to combine their security efforts and make the overall system, and therefore their overall security, much stronger at a relatively substantially lower cost. It provides interoperability. This is important if we are to get various different economies interacting with each other. It allows the different blockchains to communicate and collaborate between each other by virtue of a common language. The common language in this case is XCM, Cross Consensus Message Format. And as I mentioned, blockchain provides data availability inherently within the system. No additional costs are needed, no secondary token. Now that's Polkadot, but how are we actually turning Polkadot into the Web3 cloud? How are we developing this? Well, the first thing that you do when you're trying to build a cloud is you start off with a hefty machine, a powerful machine. The second thing you do is you make lots of these machines and connect them all to each other. We're not dealing with real machines, of course. We're dealing with these strange, decentralized machines. So we start off by creating a decentralized supercomputer. We have a name for this decentralized supercomputer, or at least a protocol that allows the decentralized supercomputer to manifest itself. It's called Jam. We also have mechanisms for taking multiple instances of Jam, connecting them to each other in some actually useful way, and then averting the need or averting the problem of having lowered security because of it. So Jam, what is it? Well, in some sense, it's the latest iteration of Polkadot. It's actually specified in a paper not dissimilar to the yellow paper, as Obi mentioned, Ethereum's formal specification that I wrote back in 2014. It has a similar format, and anyone who's familiar with the yellow paper should be reasonably at home with the grey paper. By implementing the grey paper, there's a pretty strong incentive that you get to partake in. 10 million DOT has been placed in a prize pool for teams implementing the grey paper, implementing this supercomputer, decentralized supercomputer protocol. Now, in addition to being able to claim a portion of this prize pot, you get some additional support, such as on-chain salaries in stablecoins, professional audits for your software, invitations to international seminars with other people that are implementing. You get access to hardware for testing out your implementation on real sort of validator hardware. And very interestingly, you get access to the Jam toaster. I'm going to get onto that in a second, but first I'll let you know 36 teams have currently declared their status as implementing the grey paper, implementing Jam. And some of these teams are pretty big. We know at least one with 7 or 8 people in it. A number of different programming languages are being used to implement Jam, 15 at the last count. And this gives us that diversity that helps Jam be anti-fragile, not merely resilient, but actually benefiting from diversity and decentralization. So the Jam toaster, what is it? Well, here's the thing. When you start coming up with these complicated protocols, decentralized protocols and complex decentralized protocols tend to have, or it tends to be the emergent effect of the protocol that you're after, that you want to happen, that you're counting on being correct, that you're counting on doing what you, or having the effect of providing the service that you actually want. When you're implementing normal, traditional protocols, the code that you write is generally the thing that will provide the service that you are aiming for. And therefore, there's a very clear mapping between the service that you want to provide and the code that you need to write. This is what makes it so easy to write centralized protocols. This is why, when you're coming up with a service, your natural instinct will be to write it in a centralized way. Because you can very easily put yourself in the position of the computer that's running the code. You think of the service that you want to happen, you pretend you're the computer who's running the code for that service, and you just sort of write out what it is that you would do. This makes it easy also to debug the service, because you already understand what it is that the code should be doing. And therefore, you can go through and work out where it is that it's doing something different to what it is that you would do if you were the service. It's different if we are using decentralized game theoretic services whose actual utility isn't directly what the code is doing, but rather the emergent effect of what happens when it interacts with, say, 1,000 other instances of code doing something. Yeah? Because what we're counting on isn't the direct effect. What we're trying to solve the problem of isn't the direct effect, but rather this indirect effect. Now, when you're engineering these systems, as mathematicians, we can relatively easily predict the emergent effects. The security behavior, for example, or the speed that a system should go through. We can model this and we can theorize about it, and we have good tools in mathematics to be able to work out what these things, how these systems will work. Or rather, how they should work. But when we engineer systems for emergent effects, things can go a bit wrong. Because debuggers don't work in terms of 1,023 decentralized node operators software running on random hardware, right? There is no debugger in the world that could debug the Polkadot network as a whole as it stands. This just doesn't exist. This concept doesn't really exist either. No one's tried to engineer this before. Now, if the emergent effects are relatively sophisticated, we end up with a pretty big problem. How do we debug these systems? How do we optimize these systems? How do we analyze what's going on? It becomes hard. And what we do is we tend to find an environment that we have control over, and we simulate what happens when 1,000 nodes will interact. We try to simulate the emergent effect and then analyze the simulation. And this can work okay. Now, the problem is that if the simulation significantly diverges from the reality, we still have a problem because our analysis will be incomplete. We're only dealing with a model. For example, if we set up a test net of, say, 6 nodes and try to debug the same thing that happened on the main net of 1,000 nodes on this 6-node test net, it's quite possible that we won't see the same emergent effects because the parameters are different. The same goes with the networking. If the network is perfect on our test rig, we're probably not going to see the same emergent effects as the imperfect networking in reality. So really what we need is a custom-made testing and experimentation system that can, for all intents and purposes, emulate perfectly the conditions of the production network. But with one additional thing, of course, that we can connect our debugging tools to all of the nodes and get a full depth of information. We can essentially, we're not stuck with looking at the trees, one tree and another tree and another tree, and trying to work out why the forest is not thriving as we expect. Instead, we can analyze the forest as a whole. And that's really what the toaster is here for. It's a small supercomputer. It's not really comparable to modern supercomputers, particularly not GPU ones, but it's nonetheless not a regular computer. It has 16,500 cores. It can process an awful lot of information. 32 terabytes of RAM, and 20 petabytes of secondary storage. NVMe secondary storage as well. Fast stuff. It's being built in a custom location, a single location where we can actually connect effective logging systems to it and get deep analysis of the emergent effects. And it's only really with this kind of systematic way of optimizing that we could really expect a system like Jam, once it's deployed in the wild, to run at the speed that we as mathematicians and theorists expect it can run at. Okay, so that's the approach that we're taking with Jam. And in blockchain these days, it's a pretty novel approach. What is Jam? I drew a little picture of, well, a sort of visualization of Jam. It's that's the little flower under the logo there. I drew it with 5 leaves. In reality, Jam has 341 leaves, but you get the picture. It's kind of a quite particular structure. To understand Jam, you need to understand a little bit of what we're trying to solve. Web3 systems have to be resilient. This is the crucial difference, as I mentioned, between Web3 and what came before Web3. There are some other qualities that we also want from Web3 systems. One of them is generality. This is a quality that Ethereum took a big step in. Another is performance. This is a quality that Polkadot took a big step in, as well as generality. But where Polkadot brought high performance, one thing that it lessened was coherency. All systems need accessibility, which is essentially to say that people need to be able to access these systems, be able to use them. So let's go back. Performance, coherency. Polkadot has performance, but less coherency. Obviously, Ethereum has not so great performance, but is fully coherent. What do we mean by coherency? For this, I'm going to draw some pictures. So, Ethereum 1. Here's a picture of Ethereum 1. It's not scalable. This is the main problem with it. It was a good experiment. It showed us what's possible with smart contracts, but it's sort of demonstrated that if we're going to do anything serious on these systems, we need to improve how many people can use it and what costs they're facing. One way of trying to solve this, of course, is to increase the overall requirements of every computer that is expected to be able to utilize or host the network. We can scale it up. We can keep the model more or less the same, but scale it up and find all sorts of different optimizations in the execution system, in the languages that we're using, in the networking that we're using, in order to try to make it go as fast as possible. This isn't a particularly good plan. It will get you some short-term gains, of course, but they'll generally come at the expense of longer-term, important principles. You'll generally find your network is centralized, or more centralized than it should be. You'll generally find that your network is fragile. These software optimizations don't come at the cost of nothing. They generally mean that by having very, very particular, specific optimizations, you're probably going to have just one client that can actually run this, one piece of software, one development team. And all of that knowledge, all of those little tricky bits that you need to understand will be in the minds of only 1 or 2 or 3 people. If they happen to be ill one day when there's some code change going through into the code base, you're kind of screwed. Ultimately, of course, the scaling up is not scaling. You will hit a ceiling. The ceiling will be, the end game for this is having a single computer that's just really, really fast, just a supercomputer. And you just run everything through the single supercomputer, and no one can really hope to keep up with that supercomputer. Yeah, that's the end game. That's not Web3, and to be fair, it's not really even scalable. Supercomputers have their limits. Okay, so another way of doing it is say, well, if one chain is limited in terms of how many transactions it can process, why don't we just have several chains? We can connect them together in some way. This is what I call homogeneous bridged chains. Basically chains that do more or less the same thing, act in more or less the same way, but they have bridges between them. Now, the problem with this is that there is a significant, what I call a state partitioning. Well, actually, the first problem is it's insecure. Those bridges operate outside of the consensus system. There is no overall consensus system that they can operate in. So they kind of have to operate in a bilateral fashion. Effectively, the bridges are only as secure as the weaker of the two endpoints. Now, if all of your blockchains are really, really secure, that's not such a big problem. But if we want to scale this out, then we're going to end up with the capital that is required to secure these chains also to be scaled out. And that means the capital ends up getting split between these chains. We end up having some sort of decentralization, but it costs us the division of security. Now, there's also another problem with this, which is that each of the chains are basically walled gardens or silos. They can interact with things within the chain, but they don't interact so well with things outside of the chain, like other chains. If you want to atomically compose two smart contracts that live on different chains, you're basically screwed. Especially in this system, because there isn't a single place that you can go to and ask what the actual place in the chain is, like where the finality is. Each chain has its own. There's also some high barriers to entry if we're developing and deploying a whole blockchain. We have to find validators for it. We can also look at Ethereum. One of the plans for Ethereum, it's a while back now, is they've changed it since I think about a month or so to native rollups instead of L2 rollups. It's hard to keep up sometimes. But the problem with having multiple different rollups, which is essentially the situation that is on Ethereum at the moment, is that it's patchy. The different rollups have different properties. They may have different versions of the EVM, they may provide different security characteristics, they may have different centralization biases, they may have different latencies of finalization, they may have different ways of communicating with each other or with the Ethereum, the main chain, L1. In addition to that, there's also still this persistent state partitioning. If two things happen to be in the same L2, they can interact that much easier than if they're in different L2s. L2 rollups, particularly ZK ones, also tend to be pretty centralized, sometimes with only a single sequencer. You don't need to look too far to see that many of the common L2s on Ethereum are of substandard level of centralization. And we can also mention Polkadot, the original sort of Polkadot idea, relay chain and parachains. This also has the problem of persistent state partitioning. If you're on one parachain, then you're not on another parachain. If you want to deploy a contract to, say, Moonbeam, then that's fine for interacting with the rest of Moonbeam, but it's a bit of a problem if you want to interact with Astar or whatever. Now, there's also some high barriers to entry because, of course, you're developing and deploying your own blockchain. They're lower than Cosmos because you don't have to find your own validator set. You only need collators, which is a relatively less important set of actors. It doesn't have such a malicious collator, doesn't have such a significant effect on your security, but still, it's the barriers are there, and they're higher than they would be if you're deploying a smart contract. So let's talk a little bit about why we see persistent state partitioning in these systems. Now, the reality, it turns out, is that some decoherence is unavoidable if we want to scale the system, and certainly if we want to keep it decentralized. Now, I say size synchrony antagonism, I could also say size coherency antagonism. Essentially, as a system scales out, If we want it to keep going at the same speed, we have to lose some coherence. The reason is very simple. There is a finite speed of light. There is a finite speed of cause-effect. Cause and effect doesn't happen instantaneously over a large distance, right? It has a time. The effects take time. Now, if we built photonic systems and it was totally centralized, we could probably get very, very fast computational systems. But these are not photonic systems and they're not centralized. They're decentralized systems, which means we'd have to do quite a lot of game theoretical faffing around or cryptographic faffing around. And everything works at least within the machine on the electron level. And electrons are a lot slower than photons. And so what we end up with is a need to work out how to manage this loss of coherence. Now, the way that we've managed this loss of coherence industry-wide thus far is by splitting the overall system up into bits, independent parts that can be fast, reasonably at least, within themselves, but slow when they're going between each other. Yeah? This is just how we've solved the problem. We just carve the overall state up into partitions. And we call these partitions L2s or parachains or blockchains. But in reality, all we're doing is taking the overall state as a whole, like the overall state of Polkadot, or the overall state of all the Ethereum L2s and Ethereum, and carving it up. And we just say that they're coherent within themselves, but not so coherent between themselves. This is really what we want. So I'm using a slightly nuanced visual language here. I want to explain it to you. The outer border is the overall state of the system. The arrows are basically arrows of time. As we compute, as an actor or a smart contract or whatever, some piece of state sort of goes ahead and does its thing, we're going down. Now, the fact that the arrows have this orange background and the fact that they are going all the way from the top to the bottom indicates unbroken computation that has normal memory access. And this is really what we want. And the fact they all live in the same box, right? There's nothing between them, indicates that they're all, in principle, atomically composable. They can all interact with each other whenever and however they want. This is the ideal situation. Obviously not just with 9 arrows, but with infinite arrows. But I couldn't draw infinite arrows, so we're stuck with 9. This is the ideal. This will never happen, by the way. Size, synchrony, antagonism prevents this from happening. We can't have infinite synchronous processes sharing all the same state. Like physics won't let that happen. But it's what we would like. So the question is, how close can we get and what do we have at the moment? Well, here's Ethereum 1. It has a few arrows and then not very much happening and then a few more arrows. And if you notice, the arrows are not side by side. It kind of does one thing and then it jumps to do another thing and then maybe it goes back and does more of the first thing. And there's a lot of space in there. The reason is that actually Ethereum spends most of its time not really doing anything. If you run an Ethereum node, then other than sending and receiving messages and maybe maintaining the transaction pool, it won't actually be spending that long executing the transactions, right? On my a regular sort of machine, in my reckoning, will spend at worst, like in the worst possible case, the block that has the most transactions in that are doing the most slow stuff, about 1 second in every 15. 14 seconds out of every 15 is idle. It's not processing transactions. Now, this is for a particular reason. We want to, when we're designing Ethereum, we wanted to make sure that it was secure and that someone running a low power node would be able to synchronize and so on. There are various reasons for when you're building a sort of decentralized network where everything has to process everything else, everyone has to process everything, I should say, that you leave a lot of room, right? A lot of headspace. It's not ideal though, right? It's not close to our ideal system. And if you notice, these arrows are short, whereas these arrows are long. They go all the way from top to bottom. These arrows just go a little bit, indicating that the execution is very short-lived, right? Everything has to go into secondary storage and then come back out again when it restarts. This is the notion of a transactional compute system. Yeah, it's like you can store things in secondary storage, sure, but all of the bits of working memory, they get thrown away, and you just have to start from scratch every time. Every time you get a new bit of information from the outside world, start from scratch. This is not an ideal situation, and it's certainly not the situation that most software developers are used to. Now, if we only process one of these things at once, basically if the arrows are sort of jumping around and never overlap, then we can actually simplify this and just say there's actually one arrow that goes the entire length that the short arrows go. Because it doesn't matter if it's sort of several short arrows each processing different parts of the state, or one arrow that just has access to all the state. Yeah? So high-performance synchronous networks, of which Solana would be a pretty good example, but there are many others that just try to carry on with this roughly the same model, but have a lot of optimizations to try and make it go faster and generally use the time in a more optimal fashion. Might look a bit like this. I've drawn the arrows thicker because there might be, for example, the ability to use multiple cores on a CPU at the same time. Yeah. Still, every machine that is on the network has to do this multi-core computation, but there may be some ability to parallelize, and might be that, or it might be in other cases that the virtual machine goes a bit faster or whatever. And again, we can simplify this to basically just being one thick arrow. You'll notice there's a bit less space between the two arrows. This is because we're now working, the one thick arrow indicates block execution, right? But they are disjoint, right? We execute one block, throw away all the working memory, all the sort of incomplete calculations, they all go, unless we explicitly place them into secondary storage. But generally, we're not going to do that. And we have to write our software very particularly if we expect to. And then we start again on the next block. So, Cosmos, what's Cosmos doing? So this is independent blockchain network. So each network basically is wholly independent. If we wanted to, we could launch a network. We don't have to ask anyone's permission. And then it's like, well, actually, maybe I want to talk to the other networks. Maybe I want to somehow asynchronously compose my application with other networks. Okay, then we introduce a bridge. Maybe we're sort of in the middle of the network and we have lots and lots of bridges. Now, the problem with this is, of course, that decentralization comes at the division of security, unless you're going to do something that is not yet done, which is try to share the security. What happens if we share the security? Well, then we end up with something that's the Polkadot 1, right? The ability to share the security between different economies in some totally transparent way. Now, I've drawn the dotted lines are basically the message passing system that allows different Polkadot parachains to pass messages with a little bit of latency. But you'll see there's a few non-dotted lines, solid lines. These are like bars that run all the way from top to bottom. And these bars denote the fact that they're not sharing the same state. They're in their own state partition. Parachains have some state, and it's not other parachains' state. Of course, there can be some sort of oracleized proof mechanism for basically allowing them to read other parachains' state, like they might read the price of the dollar or whatever. But this is not part of the system. The system, the model as a whole, is that the state is partitioned. Parachains have their own state, and when they want to alter that state, it's the parachain's logic that alters the state, not any other parachain. We also see the break. We run for a block, pack everything up, stop. When the next block comes along, we start again, unpack everything, and continue where we left off. There is no concept of working memory just being continuous. We have to pack everything up. And this is something that is actually quite problematic. If we're doing something, for example, like a storage migration, if you can't get through the whole storage migration in a single block, like, how do you manage that? Your system is going to be kind of halfway migrated. You have to do all sorts of strange things in order to, and think very hard about the problem, in order to make multi-block storage migrations work. This is something that Parity has pioneered, and we actually have multi-block storage migrations on Polkadot, and it's not too painful. But still, this kind of thing just wouldn't be a consideration if we had what we wanted, the ideal situation of the lines going all the way from the top to the bottom. Or, in other words, not forcing the machine to just stop and reset at every block boundary. Okay, so what's Jam? Well, in the same visual language, here is Jam. Let's start with the left. On the left, we have the data availability system, what I'm calling the decentralized distributed data lake. I call it a data lake because it's really big. It's big compared to most data availability systems. It's 1.6 petabytes. In the middle there are our coprocessors. I've drawn 4. In reality, there are 341. That's a lot of coprocessors. Each coprocessor has a big fat arrow. The coprocessor is still broken because at the end of every 5-6 second period, they reset. The big fat arrow denotes how fast our virtual machine goes. It's way faster than any blockchain virtual machine, yet the next fastest one is Polkadot's WebAssembly. These coprocessors can read from the data lake and also push data out into the data lake. In some sense, the data lake is a bit like their state. Now, it's not an arbitrary key value store. The data lake is essentially something that stores blobs of data by their hash, if you like, by a cryptographic commitment. So you can ask for something with a particular cryptographic commitment, and you can put something into it, and you'll get a cryptographic commitment back again. Yeah, but you can't choose the key. This means that you can't overwrite accidentally or otherwise any other data in the data lake. It's immutable, or at least it's immutable, but with a time limit. The time limit, for what it's worth, is 28 days. Now, those coprocessors run, and you'll see there are lines coming out of the bottom of their arrows and feeding into the right side. The right side looks more like a regular smart contract blockchain. It has the small arrows again, they're blue background. Blue background just denotes that it's a bit like, it's a fairly nuanced secondary storage model, right? The secondary storage model is essentially a key value store, but with 32-byte keys, arbitrary values. It's a bit like, I mean, Ethereum's is 32-byte keys and 32-byte values, but basically what it's getting at is that it's not very general. It's not something that you would find in a regular computer. It's not like a hard disk. It's not like a file system, right? It's quite cryptographically nuanced and pretty standard for blockchains. Now you'll notice that there isn't a blue arrow, background behind the middle arrows, the coprocessor arrows. This denotes that they're stateless, right? They don't have a secondary store, not really. I mean, they have the distributed decentralized data lake. That's their sort of secondary store, but they don't really have a regular secondary store. There's not a mutable secondary store. And you'll notice that the blue arrows, like in the previous ones, are non-overlapping. They're next to each other. Yeah, indicating that they are independent. They're separate, and the blockchain runs one at a time. Okay. So the core model. This is JAM's computational model. Now, JAM as a whole is generally coherent, but it does have transient decoherence. The transient decoherence is when these coprocessors are executing. Each executes independently of the other, and they can't see what each other are doing. That's the decoherence. But eventually they join up into the coherent regular blockchain, the synchronous blockchain, and we end up with coherence. So coherence happens basically every 6 seconds. We're a coherent blockchain every 6 seconds. Where we have sort of a period of decoherence for whatever, 5.5 seconds. This is created with a sort of a dual computation model, a dual execution environment. One of them is this really fast coprocessor execution environment, which we call in-core here. The other is the synchronous, fully coherent execution environment, the stateful one, we call on-chain here. So we have two. And every piece of work that JAM does goes through both of them. First, it goes through the really fast one, and then it goes into the slower synchronous one. And you can see that with the arrows. As I mentioned, the fast one has access to this huge data lake, very high bandwidth, I think 2 megabytes a second, with a near 6-second intercore synchronization latency. That means it takes 6 seconds for it to come out of one and then go into another. But if you're working in the same core all the time, then it's going to be instantaneous. That's why the gray arrow goes down continuously. Yeah? Sorry, not the gray arrow, the gray background to the arrow, to the white arrows. This data availability system, the data lake, stores data, all data, in 4 kilobyte segments. 4 kilobyte segments. So when you put a 4 kilobyte segment in, you get a commitment back. You can give it the commitment at a later stage, and you can get the original 4 kilobytes back. Yeah? 4 kilobytes is kind of special. It also happens to be the page size of our virtual machine. If I put them into Ethereum terms, we can also say, well, we have 341 secure, kind of Turing complete. It's not really Turing complete, but it's a Turing complete underlying language. It's still limited by the amount of computation we can do. There's a gas limit. It's very big, but it's still a gas limit. Stateless rollups. As well as one Turing complete smart contract chain that these stateless rollups sort of fold into. The rollups have common access to a 1.6 petabyte DA store, synchronized with 6-second latency, unless you're on the same core, in which case with 0 latency. How do we do this? Well, we have technology called ELVs, or as I like to call it, cynical rollups. Cynical rollups are a little bit like what Ethereum calls optimistic rollups. I don't call optimistic rollups is one of the greatest feats of marketing ever. They're not optimistic. They're pessimistic. They assume the worst possible thing, which is that there is someone lurking around who has done fraud and has a fraud proof, that fraud has happened, and there's someone who has a fraud proof, but for some reason, they have to wait 3 days, 23 hours, 59 minutes, and 45 seconds before they present that fraud proof to the network. Which means it takes 4 days before your effect in the rollup can be felt by the rest of the network. This is a very pessimistic view. Instead, ELVs for JAM, and Polkadot for what it's worth, has cynical rollups. Cynical rollups also assume that there might be people out there who are doing fraud. But instead of just kind of hanging about and assuming the worst, what we do is we actually try and check to see if there's fraud. We actually employ auditors who go around, pick work packages at random, evaluate them, and make sure that they are what the original person who, validator or whoever came along with, that it's the same. The roll-up is correct. When we've had enough randomly selected auditors do this and confirm that they've got the same result, then we know it's correct, statistically. We have adaptive near-instant finality with a system called Grandpa. What does this mean? Well, near-instant, I think you can guess. It finalizes very quickly. Adaptive. So here's the thing. If you have a regular instant finality system, like Tendermint, for example, if the network conditions degrade, you may end up with a problem that you never actually finish finalizing one block before you get the next block. And then you kind of got an issue. You either carry on trying to finalize the first block and risk descending into network traffic hell as you basically pile on more network traffic, despite it being too slow to process the first finality. Or you give up on the first one and just switch to the second one, again running the risk that you never actually complete any block's finality because it takes longer to finalize than it does to gossip a new block. This kind of system in high network traffic loads risks failing very disgracefully. Grandpa, in low traffic nodes, performs essentially the same as instant finality. But in high traffic loads, adapts optimally to finalize the most recent block, which 2/3 of nodes agree exists in their best chain. This is a pretty substantial advancement. There's a research paper on it, and it's something that should just be standard by now. Now, one of the things that is new for Jam is the PVM, Polkadot Virtual Machine. This is a fast machine. It's a pretty substantial breakthrough in reality, and it has major repercussions for blockchain, and in particular, first one at least, Jam. What is it? So PVM is an ISA based upon RISC-V. RISC-V, if you're not familiar with it, is a instruction set architecture, machine architecture if you like, that was largely invented or developed by an academic who's into this sort of thing. It's been sort of iterated on a few times. RISC-V, I guess, is the 5th iteration. And it's seen a fairly substantial amount of adoption. You can actually buy hardware processors that are RISC-V processors, right? And they just take RISC-V code and can run it quite fast. We don't require any of this hardware, but it's got pretty strong industry adoption. LLVM, for example, behind many of the sort of big compiled programming languages, C, C++, Rust, can compile directly into RISC-V as a primary target. You don't need to download weird tooling. It's not the case that you only have very particular languages to choose from. RISC-V is a solid a target for machine code. Now the Jam PVM, it looks a bit like it's derived from RISC-V, but it's different. It's derived from RISC-V, and we've kept it so that RISC-V code can trivially be recompiled into PVM code. Indeed, we have a compiler toolkit that just uses, that can just take a RISC-V code blob, executable, and just turn it into PVM, right? It's very, very simple. PVM has 13 64-bit registers, 4 kilobyte paged, 32-bit address space. It looks like a regular machine, like a regular silicon chip machine. It's Harvard architecture, so there's a little bit of a departure. Code is stored separately outside of main memory. This has a couple of advantages, particularly for blockchain, where we tend not to want code to be altered. It's a little bit too easy to accidentally alter code, and then you're kind of screwed. PVM code can be recompiled in linear time into x64 code. Code that runs on one of these natively. Linear time. This means on a blockchain, you can require all nodes to do that recompilation and you don't have a problem. You do have a problem if it's not linear time, because then someone might upload code that causes nodes to crash or take much longer than you have. PVM code can be dynamically metered with minimal overhead, maybe about 10% on our testing. Yeah? So you can do gas counting like EVM does, only costing you 10% of speed after this recompilation to native. And the PVM, it's a regular machine, so its stack is stored inside of regular memory as just regular addressable space. It doesn't have any special weirdness like WASM. We've managed to get a PVM implementation that achieves about 45% of native x64 speed. That means if you take some software, like, I don't know, a NES emulator, for example, or Doom, and you compile it to x64, and then separately you compile it to PVM, and then recompile it into native x64, the difference that they in speed that they have is only 45%. Yeah? Now this is a big deal because PVM is compatible with a consensus environment. It means that we can put code on chain that executes at a near native speed to regular code. This alters our potential programming paradigm. So in Jam, we arrange things into services. Services are like smart contracts. They're permissionless. They're code that have code and data sort of connected, encapsulated, might say. There's a bit of a difference. Services have 3 entry points as opposed to smart contracts that just have the 1. In services, the entry points are refine, which is the code that happens in the coprocessors, the big fat arrows in the middle. Accumulate, which is the code that happens in the synchronous on-chain portion, the smaller arrows on the right. And then also on transfer, which is like the message processing part of the code. Services are like smart contracts, but they have a different computation model. Firstly, the computation is staged. So there are different stages of computation. Refine, then accumulate, then maybe some on transfers. These stages are pipelined. One refine code might execute at the same time, logically speaking, as another accumulate code. Yeah? We can sort of pipeline everything together. So we end up with execution parallelism. But we can also distribute the code processing as well. Multiple refines may execute at the same time as well. So at any given point in time, Jam, for any given service on Jam, there might be any number of refines executing and also one accumulate. In addition to this difference, Jam has a different way, or services are a different way, have a different way of purchasing gas or block space or core time or whatever it is you want to call it, computation. Yeah? Now, in Ethereum, if you're familiar, transactions or smart contracts pay for their computation by buying gas. And they buy gas just in time. So right before the transaction goes ahead, whoever the sender is actually says, right, I want to call this smart contract and I want to give it this amount of gas, and it should take this price, and it should take that cost directly from my account right before executing it. Yeah, that's how it works. Just-in-time purchasing of computation. This is very different to the Polkadot model at the moment, which uses what's called core time sales, where you buy a whole month of a single Polkadot core. So instead of buying things like per transaction, I mean, you might fit, I don't know, say 1,000 transactions in every 6 seconds on a Polkadot core, right? You buy a whole just month of it, and then it's up to you how you figure out how those transactions get paid, right? Or how you make that core time be paid for. In Jam, we actually have a hybrid system that I'll talk about in a second. Further, Jam is generally asynchronous. Different services cannot call into each other purely through Jam synchronously. When they want to interact with each other, like if they transfer stuff between each other, it will be asynchronous. I'll go into that in a second. Jam is permissionless, or at least it's permissionless by design. If you instance Jam, you can obviously make it not permissionless. You can introduce permissions. That's all up to how you do things in whatever code you deploy onto Jam. Jam's really just a machine, but it's designed so that it can be permissionless. Yeah, so that it won't break if someone malicious uses it. One example of a service would be the Parachain service, or the Polkadot 1 compatibility service, yeah, that could host all parachains. That's a single service. Services are really powerful things. Jam is a machine. It's like a decentralized computer. It doesn't care about staking or economics or governance. It's not sort of a community per se, or it's not like a community engine. It doesn't really have any particular economy or staking mechanism. Okay, let's dive a little bit deeper into the technicals. So, what does it look like when you use Jam? We have 3 stages that things go through, roughly speaking. The authorization stage, which executes the authorizer code. That's one kind of code. The other kind of code is service code. So this first stage doesn't actually execute any code in the service. It can't, because we don't yet know if this service code execution is paid for, if it's what someone who paid for Jam wanted to do. So first we execute the authorizer. The authorizer is a piece of code that's not the person submitting this work package, we call it. It's like a transaction. Not the person that's submitting the work package is telling us, but rather it's coming from the person who paid for the core that this work will execute on. Yeah, that's the difference. In Ethereum, the person who pays for the work to execute is the same as the person who is deciding on what work should be done. Yeah? The person who is paying is necessarily the same as the person who is deciding on the work. They're fixed. They're the same thing. There's one account that can be in a transaction. That account gets its account balance reduced to pay for the gas, and then it's that account that decides which smart contract is called. It's in the transaction that account had to sign. Yeah? It's the same person. In Jam, it's not the same person. It doesn't really work if it's the same person, because we're selling such a bulk amount of computation. We can't really force it to be the same person. Yeah? And so instead we split it up. The service is the work to be done, but the authorizer is the thing that decides what work is allowed to be done. And then by having this separate authorizer, we're able to split apart these 2 roles, the role of paying for use of Jam and the role of actually working out what the work should be done, what the work we want to do is. So both authorize and refine happen in this in-core environment, in this co-processing environment. And then after authorize and refine, which refine is in the service code, we go into accumulate, which is also the service code, but actually happens in the on-chain environment, this synchronous environment, the environment where we can actually fold all of the refine outputs together and maybe do some asynchronous interaction with other services. All right, I'm going to try and use a few more pictures to help you understand what's going on. So, data in the Jam pipeline. Well, firstly, we might have an item. This is like a work item, right? It's like a description. It's a bit like a transaction. It doesn't have a signature, but it's a bit like a transaction. It's like a description of work we want Jam to do. It's associated with a service, which is the service that's going to do that work or define what that work is or how to do the work. A package is made up of some authorization token and some items. We can have one item, we might have many items, right? And then there's a concept of a digest. A digest is something that that comes out of this work being done on the item. Every item has a digest that's sort of associated with it. It's like what happens if you do the work of the item in refine, you end up with a digest. Digest, therefore, also associated with a service, just like items. So first we authorize. This takes the work package, which may have a number of items in, and gives you this, what do I call it, a trace, right? This is like the authorization trace. It might, for example, include the account ID of the validator who signed it, right? Or the collator who signed it, or whatever. The person who built this work package, it might have their ID in. It might have some other things in, who knows? It's just arbitrary data. Now, if we remind ourselves, a work package is really just an authorization token and a bunch of items, which means the authorized stage actually has access to this authorization, right? That might be a signature, or it might be a zero knowledge proof, or it might not be anything, but like it can be anything, and it can just help authorize figure out if this work package really is authorized. If it is something that whoever purchased this time on a Jam core actually wanted it to be used for. Next, refine. This is something that actually does the work. So we're going to take a work item. In this case, it's the red work item for the red service. And that also gets given the trace. So it can do something on the basis of the trace if it wants to. And it turns it into a digest. Okay, so far so good. It's the red digest because it's for the red service. Then we get the join thing. This isn't really represented in any of these items with an identity, an emoji, because it's part of what Jam does, just an inherent part. It's kind of fixed. And what Jam does is it sort of takes these work packages, well, they're not work packages anymore because they're the digests rather than the items, and it sorts them out by color, yeah? And it takes all the red items along with their trace, and all the yellow items along with their trace, and all the blue items along with their trace, essentially sorting it by service, right? And then it calls the accumulate of each of the services that have any digests, and it gives them each of their digests, all at the same time. It doesn't call accumulate multiple times, it calls it just once, but gives it all of the digests. So it can figure out what order, if any, it should be processing them in. It just has to figure this out. Okay, let's look at authorize. Authorize can inspect the entire package. Package includes the token, but it's invalid if the authorizer panics. If the authorizer panics, it basically just means this is not authorized. The person who paid for it did not want this kind of work to be done. If it's successful, it may provide some trace, just basic data. Refine is performed on a single item, can inspect a single, the authorized output, this trace, and it can also inspect other items in the package. It gets the other items there for free. They don't need to be oracleized in. Everything that's being processed in a package sees everything else. It has full access to everything else. This allows for some interesting co-scheduling possibilities. Co-sequencing, if you like. Inside of Refine, we can look up pre-images. We can look up data that's been placed there by the on-chain or that's been requested there by the logic that's happened in a previous blocks, accumulate and been provided from outside of the chain onto the chain. This is useful for data that is static, that doesn't change very much. And you could basically just give it a hash and it will give you the data back as long as someone has previously provided to the chain. Of course, you have to pay because every node has to store it because it's free to actually read. It can also invoke PVMs. It can create new virtual machine instances and run them, and it can do so with giving them any memory at all. This is really important. I'll go into why in a second. The limits, the sort of data and processing capabilities of Refine running in these co-processors are huge on blockchain standards. Each item can have a maximum of 12 megabytes of data. Don't forget, this is only for over 6 seconds. So every second, it can process 2 megabytes of data from the outside world. From the outside world, or also read from the decentralized distributed data lake, this massive data store that's sitting out there to the side. It can also place 12 megabytes of data into the data store to be read in any core by any service in the future. It can execute for up to around 5 seconds of PVM gas. PVM gas, remember, runs about 45% of native speed, native x64 speed, right? And we're not talking about crappy like Raspberry Pi level stuff. We're talking about AMD Threadrippers. This is a huge amount of computation. Now, items also yield up to 48 kilobytes of digest, and it's this digest which works its way into the synchronous execution environment of accumulate. So accumulate gets performed on one or more digests of a service. As I said, it gets given all of the digests that have happened recently. It can inspect all of the traces for each digest. This is also a very important security characteristic, but I'm not going to go into that quite at the moment. And it can execute for up to 10 milliseconds of PVM gas per digest. 10 milliseconds, that doesn't sound very much. The previous thing was 5 seconds. Well, yes. Unfortunately, the previous thing was parallelized distributed over a huge node network. This has to be done by every node because it's synchronous. Yeah, it's coherent. And so we have to use this computation very sparingly. Inside of Accumulate, services can transfer funds to each other, alter their own state, read other services' state, create other services, upgrade code, and run a number of other things. As I mentioned before, at this point they are asynchronous. Services are generally asynchronous. When you transfer a message to funds to another service, they happen after all of the accumulation is finished. Nothing is executed sort of synchronously. It doesn't get interrupted like it would do on Ethereum. Reading foreign state is read from the prior state before the execution began. Right, I've explained Jam. I now want to show you like what Jam is. This is a fairly sophisticated system. And you may be wondering, well, why is this, what are we doing this for? What does this facilitate? For this, I need to switch to a different machine, a Linux machine, which I am slowly doing at the moment. Right, so first I want to explain a little bit about what we're trying to solve with this initial service. An operating system. What is an operating system? On a blockchain. What does this mean? It's a very odd concept. Well, blockchain developer experience is rubbish. Yeah? If you go to university and you do a course in computer science and you learn how to program, unless the professor or lecturer or whoever is particularly interested in blockchain and is actually teaching you blockchain concepts, then you probably don't have a clue about how to code something on chain. There are very particular characteristics to writing software that will execute on chain. Your storage is weird. It's like a 32-byte to 32-byte lookup that's like uses hashes. And it's small. It's really costly. If you want to store lots of things, you're screwed. If your code is too big, you're screwed. Execution is weird. You kind of have to start and stop all the time. What happens in one transaction doesn't get fed into the next. You have no control over your sort of transaction processing loop. It's also really slow. And if you take too long, then your blockchain just stops, or your smart contract doesn't work anymore because it can't process a single transaction within the block gas limit. You've bricked yourself. Well done. You don't get a choice of languages. It's like basically there's one kind of machine code, and then there's one, or if you're really, really, really lucky, two languages that are supported. It's full of pitfalls. Lots of gotchas, lots of traps, lots of ways you might trip yourself up. We know this from 2016 with the DAO incident. And as I say, there is no continuous state, no continuous execution, like there is in basically every other execution environment. This is what we wanted. Yeah? The regular thing with lots and lots of arrows, all sort of able to talk to each other and just running from top to bottom continuously with like normal memory and storage. This is what we wanted. This isn't that. This is something else. So if I'm saying, well, this is what we want, why am I developing this? That wouldn't make much sense, would it? Well, in reality, what CoreVM does, it's built on Jam, but it gives us this. Now, this isn't the same as this. There's still the bars going down, and the way that the arrows communicate is through message passing, asynchronous. But it's closer, right? We're getting there. What is CoreVM then? It's a Jam service, right? So it's a service that sits in Jam, and it's a sequencer, which basically means it's an extra off-chain thing that helps the service go. And you can think of it like Docker for Jam. Docker for Jam. So you can load it with an executable, and it provides an encapsulation, a whole virtual machine, and it will run that executable indefinitely in that virtual machine for you in a standard environment that you know is going to work exactly as you expect. So CoreVM emulates a machine with near x64 speed. It's RISC-V compatible and therefore targetable by Rust, C, C++, or indeed anything that can target LLVM. It has paged memory, so you get just a regular 32-bit address space. Nothing special going on here. It's normal. It has continuous execution. Nothing special going on here. It's normal. Not normal for blockchain, normal for software developers. Does message passing. Comes as standard. It can run normal software, compiled from normal languages, using normal abstractions. So in this container, this kind of Docker, we can run normal software. Software that's not meant for blockchain. Software like Doom. Now, if this works, and this is the first time I've tried this. Okay, well, it might be all right. Let's have a look. Okay, I can see up here. That's good. I am going to run this little script. Now, what this script is doing is it's creating a small testnet of 6 nodes. All the nodes live on this laptop, which means they're not going to be running at full Jam speed, but it'll be enough. Those 6 nodes, which have 6 validators therefore, and 2 cores, are, let me put this window over here, there we go, are processing the Doom executable. And there is another process running which is monitoring the Jam chain and the Jam DA and feeding frames out of the DA in here. The frames are timestamped on the chain, right? And it's reading the frames from the DA that the chain is producing and according to the timestamp, displaying them in this window. So in real time right now, and you can kind of see it if you look in the background, every 6 seconds, a block is produced, which provides 6 seconds of doom frames. And we're just displaying those doom frames. This isn't a special version of Doom. This is just Doom. I just targeted it to PVM. Right? There's a little bit extra that basically is a graphics driver that just takes the virtual frame buffer and sticks it in the DA. And other than that, this is unmodified Doom. This isn't using much of a core, right? You can probably run 20 or 30 Dooms, maybe more, in a Jam core. And Jam has 341 cores. Jam is a supercomputer. You can run regular software, unmodified, on Jam. Now, this will keep going for a while yet, but I should really get along with the talk. So, unfortunately, you're going to have to tear your eyes away. Now, in principle, we could make that demo do some input as well. Like, we could have people send transactions to Jam for like how to move, right? That's just going through the regular sort of demo sequence that it does if you just run the executable. So let's have a quick review of what was happening there. Uploaded onto Jam is the core VM service. This is like Docker for Jam. Inside of Docker for Jam, there is a container that just has the Doom executable, right? Together with, I think it's core VM that has this virtual frame buffer that just uses the DA for storing frames. There's an off-chain sequencer that's basically just pinging this thing, just saying, make the next 6 seconds of frames. Now, the DA is used to read the RAM that was in this virtual machine, right? So basically, every time the virtual machine generates another 6 seconds worth of frames, at the end of that, totally without Doom's knowledge, that memory, the whole of the RAM, is being parceled up and put into Jam's DA store. At the beginning of the next one, totally unbeknown to Jam, that RAM is being read from the DA store and placed back inside the virtual machine. From Doom's perspective, nothing has changed. It's just continuous execution. In addition to this RAM that's going in and out at the end of the 6 seconds, also we output the video frames, basically the output of the graphics card into the DA as well. And because we have 12 megabytes for every 6 seconds of DA access, this is fine. Now, we have a separate process outside of Jam that's monitoring this core VM service to see when new frames have been generated. And then inside of the core VM service on the chain, it gets given the references, the cryptographic commitments to where the frames are in the DA store. And then separately it uses those to grab the frames and display them in a window. So how are we doing this? Well, Jam, we have our data lake. It's only with this massive amount of bandwidth that we could possibly do this. Like, there is no way you could execute Doom on Ethereum. We also pipeline a lot. We do one accumulate at the same time as doing another refine. And in fact, we pipeline even more than that. Our accumulate is so, even 10 milliseconds, it doesn't seem very much compared to 5 seconds, but it's actually more than we would otherwise be able to do in a synchronous system because we actually pipeline blocks. And we do this with a very special trick. Instead, for those who know about block data structures, instead of providing inside of the block header the posterior state root, a commitment to everything that the block after the block is executed, we only put in the block header the prior state root, a commitment to what it began with. This allows the author of the block and all of the other validators to execute the block more or less simultaneously. If you require the author to execute the block before they can send the header off to the other validators, they cannot do it simultaneously. And unless you're using the same validator for block after block after block, then you'll end up having this sort of, the author executes the block, sends it to the other validators execute the block, one of them then authors the next block, and you kind of alternating, right? And this means you're going to get less than half of the possible execution time. But because we do the prior state route, we can really squeeze out that amount of execution time in accumulate, in the synchronous portion. And of course, we have the PVM, which allows us to pack everything up, store it in the DA, and unpack it next block without anyone noticing, without Doom noticing. And it's fast enough, and it's a normal machine, so it can be targeted by regular software like Doom. Okay, so that's interesting, Doom on blockchain, but it's still not getting us quite to that end goal, right? That ideal. The ideal, what we are actually after, is scaling out, right? And we don't want to scale out just to rekindle your memory by having multiple chains, because that leads to fragmentation. And the problem with fragmentation is that it limits network effects. Yeah? You can enjoy the network effects within your partition, but it's hard to get the network effects outside of your partition. And it limits the use cases. And it limits the level of atomicity you can enjoy. And it limits developability. It's pain to develop applications that sit across the different partitions, across the different fragments. And also for teams developing on these systems, it forces them into a decision that they're going to be held to, because it's really hard to migrate between these things without particularly great information for their choice. This is what we wanted. Yeah? This is what we wanted. This isn't it yet. Which is why we're developing this. Now, Core VM that plays Doom is really the stepping stone. I mean, in some sense, Jam is actually the first stepping stone. Core VM is the second stepping stone. Core Play is the final destination. Core Play is a bit like Core VM, except with co-scheduling. So we can take these different executables, these different Dockers, and combine them together. So instead of having to send messages, they can be co-sequenced. They can call into each other synchronously. We can get atomicity. You might think of it as a smart contract operating system for Jam. And now we get our arrows that go from top to bottom, continuous execution, with the orange background, normal memory, normal storage, and with the ability for them to co-schedule, co-sequence, or atomically compose with whoever they want, whenever they want, with one slight, and I think very negotiable, extra consideration. The extra consideration is that it has to be economically efficient. So we're not talking about just, one or two, everyone being able to schedule with anyone else, or every smart contract being able to schedule with every other smart contract whenever they want for free. No, that will never happen. That would be this. And I've already explained to you why this is a physical impossibility. It has to be economically efficient, which means if you've got an arrow, which is basically a smart contract or a service or a Docker image or whatever, piece of software sitting on Jam inside of Core Play, if lots and lots of other bits of software want to use this, want to interact with it synchronously, then you're going to have to essentially pay your way, right? Jam will or Coreplay will naturally choose to make the co-sequencing economically efficient for the co-sequences. They will combine these arrows and co-sequence them and bring in the atomicity where it makes economic sense. But the main point is that it's not fixed. We have not fixed sets of arrows. They can move around. Yeah? It's fluid. And by being fluid, we avoid the need for teams to choose where in Coreplay space they're going to deploy. They just deploy into Coreplay space. And Coreplay will move them around as needed, or partition them up as needed. And then in the next block, partition them some other way, if needed. So we end up with what is effectively elastic, scalable smart contract environment. We can increase the number of cores available if the number of smart contracts grows. Now, there's a limit to the amount of synchronous composability you can have over 6 seconds, which is really just the limit of a core, the data I/O and data processing capabilities of a single core. But as we've seen, that's pretty high. You can do an awful lot of composition within a core. And then we just partition our state space in the most economically advantageous way, combining together smart contract actors, services, dockers, whatever, in ways that that make sense for the overall economy. And don't forget, these are not just smart contracts. The arrows went from top to bottom and had that orange background, indicating these are regular pieces of software. They can be smart contracts. There's nothing stopping you from writing an EVM, writing Solidity code and deploying it into Coreplay. It will work fine. But if you want to deploy Doom in there as well, you can. Provides effectively zero fragmentation because there is no persistent partitioning, and global atomicity as long as you're willing to pay the price. Now, how does it work? Well, basically it's by using small state atoms. We use smart contracts, actors, right? These Docker things. We don't use these hulking great blockchains as our atom. This is the main issue. If you want to have synchronous composability, you don't want to be doing it with blockchains. They're too big. We allow regular repartitioning every 6 seconds if needed. And we have an economically efficient co-scheduler that basically partitions state space up dynamically for the best economics. So why not just use regular co-sequencing? Well, as I said, blockchains are too big. Like you end up with, it's way too resource intensive to track opportunities for co-scheduling, track the entanglement, and create entangled blocks across chains and get them actually finalized. Tracking entanglement in particular is a problem unless all of your chains operate under basically the same environment, because it becomes an order n squared problem. Every chain has to track the possible entangled effects of every other chain. If one chain finalizes without the other chains finalizing the entangled transaction, they're screwed. Or even worse, if all of the chains but one, well, not even worse, but accordingly, if all of the chains but one finalized and one didn't, they would all be screwed. You only can either do none of the entangled chains or all of the entangled chains. Yeah? And this makes it unscalable. You might just about be able to make it work for a couple of chains or 3 chains if you scale up your validator nodes and have an awful lot of validator network support. But making it work with 341 chains, that's hard. And this comes with a huge centralization bias. The machines needed to actually track the opportunity for co-scheduling across these huge state machines that are blockchains is it's a huge amount. You need vast amounts of network, vast amounts of computation, and it all has to sit in the same machine, which means it's a winner-takes-all situation. There's not that many people that this could possibly fund. It's going to be realistically financed by 1, maybe 2 outfits. and which this creates further problems if we want actual Web3 guarantees. What about intent solvers? Well, basically intent solvers solve a different problem. They're not about allowing the composition of smart contracts or services within a consensus environment or between consensus environments. They're more about figuring out the right sort of set of transactions to do to affect an overall solution. They're essentially a patch for a very fragmented system rather than a fix for that fragmentation. And can we not just have multiple instances of like the same code on different networks or different L2s or parachains or whatever? No. There's no network effects. The capital will always sit in one place at one time. Why are we not using ZK? I get asked this a bit. Well, the simple situation, there's a couple of answers. One of them is we are using ZK. We're using it for our block production algorithm to ensure that it's secure, that you can't predict who the next producer will be until they produce the block and it's already out. This is important, an important security consideration that other networks, I could name one, but I'm not going to be nasty, like to disregard. However, we don't use it for scaling computation. Now, the mathematician in me, of course, thinks that this would be a very nice, pure, clean way of scaling computation. But the problem is that it's just not there yet. Maybe it will be there in some years to come, but right now, the cost associated with ZK to generate a ZK proof and even verify a ZK proof is massive compared to the cost for running cryptoeconomic games to achieve the same thing. The cost, for what it's worth, we calculated as around 2 million X, although that was a year ago. So it's probably come down a little bit, but still, it's orders of magnitude more expensive. Some theorists think that it might get down to being comparable. Other theorists, in particular the research group at the Web3 Foundation, think probably not, that it will probably stay 4 or 5 orders of magnitude. That's where that will likely be its low point. We'll see. Of course, we'll keep our eyes open for improvements in the space, but right now, ZK is not a scaling solution that makes economic sense. Good. That's the talk. Hope you enjoyed it. I have more demo, but I don't know. Maybe you demoed out. Yeah. What do you think?
Yeah, 5 minutes.
5 minutes. All right. Let's do a quick demo. So you've seen Jam, doing its fun thing. I'm going to give a quick demo of sort of developing on Jam. As you remember, Jam has this multi-stage step, refine, accumulate. Here I have a Jam sort of terminal, if you like, a Jam REPL. I'm going to make it a bit bigger so maybe you can see a bit easier. Can you see that? Is that okay? Can you read that? Yeah.
First liners, yes.
Yeah, first liners. Okay, let me see if I can make it bigger still. Right. Okay, so Jam has, as I mentioned, services. We can list the services with ls, and there we go. We've only got one service. This is the Bootstrap service. This is a service that allows you to do various actions that might be useful to do on Jam. It's sort of like the administrator service. When you start a Jam chain, Jam doesn't have any inherent features for creating services. It's just literally, it's like a bare metal CPU. Yeah, it processes computation, but there's no way of like actually introducing software onto it. So you kind of have to start with software already on it. It's a little bit like, in fact, it's quite a lot like a BIOS or whatever UEFI firmware inside of a regular computer, right? It's the bit of software the CPU executes at the beginning that you can load the operating system from and the various software from beyond then, yeah? And so essentially we have this exact service, call it the Bootstrap service for obvious reasons. It has a nice fat balance and it does kind of everything that we might need it to do. We can inspect a service, I think it's IS, and then we give it the service ID, and it will tell us a bit more about the service. So we can see that, look, it's got some balance and there's some threshold. And we can see that there's some code in there. It's 80K and so on. We can send transactions to this service. For example, I could send it some data. I can create a work item, like for example, hello, and then send it to this service. I think by default it sends it to the default service, which is the Bootstrap service, and guarantee the block, which will basically execute this item. Of course, it's not going to do anything. It will just say, don't know what this hello. I have no idea what hello means, and this is the thing that means that. Just sort of panicked. There's a bunch of commands inside of this CLI that allow me to construct sensible things for the Bootstrap service. One of them is the create service command. And this will send the Bootstrap service a command that will then tell it to create a new service. To tell it which service is created, I need to give it a file or some data. It turns out that there is already a service that I've compiled called the demo service.pvm. Let's have a quick look at what that code looks like. Here we are. Actually, I think there's maybe another one. No. Here? No. Okay, never mind. Right. Demo service. Bear with me a second. I think it's that. No, it's that. Main. Demo service. Okay. So, you probably can't read that at all. So let me make it bigger for you. Right. So, this is what a service looks like in Jam. I mentioned before, services have 3 entry points: refine, accumulate, and then on transfer, which doesn't really, just message processing. So refine, what's a refine doing? Well, it takes the service ID. Like we need to know, that's kind of like the this pointer or self or whatever. It's like the identity of the service itself, rather than just the code, and the payload, which is the data, right? It's like the transaction body, the data that's coming in from the outside world. There's a few other bits that we get, but we're not going to use those. We also have the authentication output. That's the trace, right? The thing from the authenticator that tells us that it's definitely legit. And we're going to make a message after making a debug statement. We're just mentioning the payload and the authentication output. And we're going to export that into the DA. So that's what it looks like to export something into the DA. And then pass the rest of it on into accumulate. Inside of accumulate, we'll process all the items. We're probably just going to be one of them. Decode this data to get back these original 3 things and stick them in storage. So we've got 3 storage items: last info ID, last payload, and last auth output. Basically just the reference into the DA, the payload data, and the authorization output. Very, very simple service. Doesn't really do anything that interesting, but it'll do for a demo. So we're going to create this service. We're going to pass it some funds to begin with, because it will need more than the minimum amount, because we're going to store some data in its storage. So we'll give it like plenty of fun, maybe not that much. There we go. And there we go. So we can already see it's doing something with Jam, right? It's passing through the null authorizer. This is just the authorizer that authorizes basically everything, as long as the parameter into the authorizer and the token that we pass in the work package are the same. In this case, they're definitely the same because it's empty. Both of them are empty. We go on into the Bootstrap refine, and this is where we're doing that. Now you see it hasn't panicked. It's doing something useful. It understands what it's being told to do. And we've gone on to guaranteeing the work package. We're going into accumulate, and it's telling us it's created some sort of service here. We know that's our demo service because that's what we told it to create. And there we go. It's changed the default service now. So let's have a look at the services. We can do that with ls. And of course, yes, there are 2 services: service 0, the original Bootstrap service, and now the default service is service A. It gives us these letter things, so it's like a pain to type the big number thing. But it's we can type either. The CLI understands both. And it's telling us there that, yeah, we've got this demo service. And if we want, we can inspect it a bit more. We can inspect service A, and it will tell us a bit more about it. Okay, now let's send it some work. So if we go back, we know we can do make a work package by telling it, well, we want to take a work item. So let's do work item. And we're going to say, just give it a nice message. We'll say, hello, Shanghai. Okay. Okay, and it's basically queued that up so that when we actually parcel it up into a work package, that will go in there. We can then guarantee it. So let's guarantee, and that will then take these work items, there's only one, and send it into the default service, which at the moment is this new service, demo service. And let's see what happens. Okay. It looks like it's worked because we've got debug messages saying that this is refine in the demo service and this is accumulate in the demo service. Now, if it's worked, there should be a few things that have happened. The first thing that's happened is, let's have a look at the code again. It should have written these 3 storage items, last info ID, last payload, last auth output. Let's have a look at those. Last info ID, we can read storage with read storage, which is in here somewhere. There we go. We can also read it with just R. Anyway, last, what was it? Last payload. Let's try last payload. And hello, Shanghai. All right, so this has worked. It's gone through the code, written it into storage. It's all good. Let's read a few of the other things. Last auth output, I think it was. And there we go. It's given us this auth equals empty. We know the authorization token is empty. It turns out that the null authorizer, I can probably actually show you the code. Let's have a look at the null authorizer code, which is the code that it's running. Null authorizer main. So this is what an authorizer looks like. Very, very simple. It's just checking that the parameter to the authorizer is the same as the authorization token. It's a silly little check that I put in. And then it's making a message that it's outputting. That's the authorizer output, the trace. Auth equals, and then whatever these the authorization was. Our authorization is the empty string, so this is just going to be empty. And of course, yes, that's what we get. So the final thing that we want to look at is the last info ID. This is where it put in the DA the message that we concocted telling us about the payload and the authorizer. 0, it's saying. So it's item 0 in the DA for this work package. So let's look in the DA. I think we can actually read a segment from the DA. We have to tell it the block number, which is 2. Which one was it? It would have been 5, 6, maybe. No. Actually, let's just look in the DA. We actually have a list segment trees, which is basically lets us list out the contents of the DA. Now we should see in one of the in the most recent one, the only one that actually has any items, numbers are 0. The 0th item should be that message. And if we look at the format of the message again, the format of the message was last auth output. It's coming from in here. It should be payload : the payload auth output : the auth output. Let's have a look and see if that's what we get. And yes, indeed we do. So we've found that the work package 0x5a blah, blah, blah has this segment root, 1 export, 0th export, same as there, payload, hello Shanghai, auth output, and then that auth output. I think I'll switch to questions now. I think that's a good point to stop.
Thank you very much for introducing to us Gem, truly first of its kind. Thank you so much. Please,
Cheers.
let's give Gavin a round of applause.